I'm Daniele Perossa from the IRTC Junior Board, and today I have the pleasure of, first of all, introducing the speakers. So Professor Christoph Helbig, who is Professor of Ecological Resource Technology at University of Bayreuth in Germany. He gained his PhD in Industrial Engineering at University of Augsburg in Germany. Since 2019, he is a JSPC postdoctoral visiting researcher at Waseda University in Tokyo, Japan. And in 2023, he received a Laudize Medal awarded by the International Society for Industrial Ecology for outstanding industrial ecology research by researchers under the age of 36. And then we have Mr. Jan Kosmol, who is a scientific policy advisor at German Environment Agency since 2009, and where he works on environmental criticality of raw materials from mining, environmental due diligence in mineral and metal supply chains, and in green and just circular economy topics. His tasks include the provision of scientific policy advice to the German federal government, and is active in various boards and committees, including the role of chair in the International Expert Working Group on environmental due diligence in mineral supply chains at OECD between 2029 and 2023. So now, without further waiting, I will hand over to our speakers and wish you all an interesting and entertaining webinar. Thank you.
Thank you very much, Daniele. Thanks a lot for the kind introduction. And yeah, thanks also for having us, also on behalf of Jan, who will speak a bit later. So good afternoon, everyone, wherever you are. We have this webinar here now on critical raw materials and the environmental transition as a pre-webinar before the big IRTC conference later next month. And we envisioned this session here today to give you a little bit of an overview on what critical raw materials demand looks like, what is how that translates to also clean energy technologies. Then in the second part, Jan will give you an overview on environmental impacts of critical raw materials production. So we turn around the perspective a little bit. And then in the third part, we'll take things together and look at mitigation options for environmental impacts. So what can we do? And we hope that we will still leave that like a quarter of an hour at the end for discussion in the remaining time of the hour that we have now. So without further ado, I would like to start with the first part. And I would like to start with a recent result from Austrian colleagues together with a larger consortium where I was part in. And as you can see here from the slide number A here in the top left, we're growing large stocks as anthropogenic stocks. So over the past century and a bit, we have grown the anthropogenic stocks of products, of buildings, of bridges, roads, to over 1,000 gigatons. More than half of the material production globally, overall material types, goes into expanding that in-use stock of products and not into replacing other materials. This led Friedrich Krausmann and colleagues also to the statement that we are actually in a stockpiling society, not in a throwaway society. Of course, a lot of that, of those stocks are buildings, civil engineering, and roads. But as we can see from the bottom two graphs, it's also a lot of machinery, vehicles, computers, electrical equipment, and other products. And many of those rely on metals and critical raw materials for them to be made. And also for them, the in-use stocks are drastically increasing. One part of the reason for that is, of course, the global increase of production of raw materials. We have seen this here on the left for iron and steel already. You can see historic production rates until like the year 2015, roughly. And then from this excellent work from Takuma Watari and colleagues, a projection as a meta-analysis over a variety of studies of how much material we will need in 2030, 2050, or the end of the century. And of course, you can see that there's a range. Projections can always differ, scenarios can differ, but overall, the anticipation is that for these kinds of base metals, the global material demand will continue to increase. That is even more the case for aluminum that you see on the right side, which we basically only started to use in the 50s of the last century and have drastically increased the production rates recently because of lightweighting and other application ranges. There, the production rates are growing even faster than for iron and steel. But it is also the case for critical raw materials. So we can go all the way through the periodic table in this rough estimation, and we see a repeating pattern that most studies estimate that the overall demand for these materials is going to increase. You see this for materials that are typically not considered critical raw materials, at least not in the European Union. On the left side here in blue, and on the right side in red, you see that for critical and strategic raw materials already, where again, a large increase until 2030 or 2050 is anticipated throughout the studies. But this is just a meta-analysis. Why is this the case? Well, first of all, because of strategic technologies. So the European Commission has identified, together with the Joint Research Center, a range of technologies that are relevant for strategic sectors. And 3 of those strategic sectors are directly linked to the environmental transition. We do have electrification technologies, like lithium-ion batteries that are directly relevant for storing electrical energy, but also technologies for electrifying previous technologies which relied on combustion of fossil fuels, where we have, for example, traction motors, which should be electric motors in the future, or heat pumps replacing maybe our gas boilers, etc. We also have directly renewable energy, wind turbines and solar photovoltaics, which are identified as strategic technologies. And we have the whole thing of hydrogen economy that goes to electrolyzers and fuel cells. So switching energy storage type between electricity and hydrogen directly, one way or the other, and using that hydrogen to replace other raw materials, for example, replace coking coal in steel production, where then hydrogen would be the reduction agent. There are other strategic technologies as well, just to mention that, but these are resemble mostly around digital technologies in aerospace and defense, so not that much maybe around the energy, the environmental transition. And that has led the JRC to look at the global demand for these technologies and assess that in comparison with previous demands for those technologies. And you see this here already sorted, lithium here very much at the bottom, where we see a multitude of 2020 demand as the demand which is anticipated for 2030 or 2040. Of course, there's different scenarios on the left and on the right side, and you can compare that then throughout those strategic materials, graphite, cobalt, nickel, where things then get less and less drastic or less and less important. But again and again, there's a repeating pattern of increased demands. So this is the JRC internal view, but we can also look at this from the works of the International Energy Agency. There they looked at global demand for various critical raw materials or potentially critical raw materials. They went on copper, lithium, nickel, cobalt, graphite, and rare earths. So partially this is about electrification, partially this is about batteries, partially this is about magnets, mostly, when we go to this to these raw materials. And one thing that I would like to stress here is not only this increase where we have 2, 3, or up to 9 times as many raw materials that we need in 2 decades compared to previous levels of demand, but also this shift. For example, look at this shift here for nickel in the middle, where previously nickel was mostly used for making stainless steel. We now have a drastic shift that nickel will be more and more required for batteries, and therefore the whole market changes. So also the perspectives changes, and who's is a core role and who is more like the side sector, the importance shifts. And we see that for various technologies. We have seen it for lithium in the past already, where basically lithium is now completely dominated by the battery sector. As a last example, there was also the very nice study from KU Leuven and a commission from Eurometaux, so the European Mining Association, which looked at another range of critical raw materials or potentially critical raw materials throughout 2 scenarios and compared the raw material demand here. And the learning here from this graph is that even if these numbers for 10 times as much lithium, for example, or 9 times as much lithium as previously, it is still going to be aluminum and copper in terms of the mass of the material that is more important. And even if the growth rates there are a little bit slower, then they still are going to be mass-wise the dominant, and that could potentially also relate to the environmental impacts. So closing for this first section, we are in a stockpiling society which basically hoards anthropogenic stocks, which can also be a positive side, but we'll come back to that on the third part. We need those critical and potentially critical raw materials for strategic sectors like renewable energy, electric mobility, clean industries, hydrogen economy, and they need a variety of critical raw materials, quite a range, all the way from lithium to neodymium. And if we look until the demand until 2030 or 2050, well, 2030 is just 5 years in the future. 2050 is still quite far in the future. We can see increases of factors like 1.5 or up to 15 times the 2020 demand levels, which is a drastic change and which requires continuous improvements in terms of the production volume and expansion, also in terms of mining and refining, which then, of course, may lead to a challenge. And with that, I will hand over to Jan for the second part.
Yes, thank you very much, Christoph. Yes, this demand increase must be supplied by mining and primary mineral smelting and refining to metals, because recycling can only feed back what is already in use in these stocks, and additional raw material demand needs to be fed by primary mining and metal smelting. And these activities are quite relevant from an environmental perspective. We can say those are high-risk sectors when it comes to environmental impacts. And I brought you here a figure from the OECD. It's from the OECD guidelines for multinational enterprises on responsible business conduct. And there's a grievance systems in there, and it lists all grievance cases since 2011, all grievance cases which cite the environment chapter of these guidelines for enterprises. And 39% of all these cases referencing the environment chapter relate to the mining and quarrying sector. Another figure, and smelting is in the manufacturing sector, it's the second one. Another figure is the global mercury emissions by artisanal small-scale and small-scale gold mining are about 38%. The rest is coal combustion and other effects. And when it comes to energy use and climate, mineral and metal production is also very relevant. There are different estimations, but this more recent one from Azadi says that it's estimated about 10% of energy-related greenhouse gas emissions are from mineral and metal production. However, you need to know this is mostly from smelting and mostly from steel smelting, bulk materials. So next slide, please. And For this reason, environmental aspects have been discussed in context with criticality for quite a while. The first study by the EU on critical raw materials from 2010 had an indicator called environmental country risk. The approach was to have it in a third dimension, besides economic importance and supply risks. And it was measured by the Yale Environmental Performance Index, which is an index which rates environmental governance of countries and their performance. So we look at the production countries of these metals, and if yes, there's low environmental performance, this index was high for a metal. But it took a very interesting perspective from my side because it looked at it that environmental protection measures that countries might take could endanger the supply of materials to the European Union. So, because yes, environmental protection might hinder a development of mining and mineral production activities. Another study was by Tom Gradle by Yale in 2012. Maybe some of you have attended the other RTC webinar in December, and that also proposed a third axis for environmental implications. Took a different approach, a more LCA-based approach, looked at specific potential impacts with a recipe endpoint characterization method, and took a different perspective. It explicitly said this is not intended to be viewed as regulatory measures to restrict the access to mineral resources, but it should be viewed as an indication for designers, government officials, policymakers, and so on to consider the environmental implications of material use. You can find more studies and how they approached environmental aspects and criticality in the paper by Duette Schreibers from the IRTC consortium from 2020. And this paper also recommends to include environmental and social implications as a separate dimension in criticality analysis in order to be able to identify and resolve possible trade-offs. And of course, there are trade-offs between environmental protection and security of supply, at least in a short-term perspective. Higher costs for environmental protection measures may turn viable reserves into unviable resources and decrease the size of a deposit, or it might even turn entire projects unprofitable. And another aspect, if we would only source from very responsible production sites, this would limit the options for sourcing. So this is in conflict with the goal of diversifying supply. But there are also synergies, at least in the mid to long term, because many conflicts around mines delay or hinder the development of these projects. And many conflicts are around environmental issues, and resolving these issues is key as a prerequisite for a secure and stable supply. Next slide, please. At the Environment Agency, we thought there's quite still some room to develop other proposals, how to include criticality, environmental aspects into criticality analysis, because both approaches have the weaknesses which I just said, and in a research project that we commissioned, another approach, a complementary approach, was developed to assess so-called environmental hazard potentials of minerals from mining. It consists of 8 indicators in 3 categories. It's geology, technology, and natural environment. These indicators are rated on a 3-step traffic light rating system by standardized measurement instruction. So it's a reproducible assessment method. It's a qualitative and semi-quantitative assessment with defined criteria, and you can do it with publicly available data. If you have more specific data, the results will get better. And just a quick view, the geology is about factors that can cause pollution, for instance, heavy metal content of the ore, radioactive content of the ore, or the potential for acid mine drainage. The technology looks at the mining method. Is it open pit, underground mining, and the use of chemicals, for instance. Next slide, please. And this third part is about the natural environment, because it matters where the mining takes place. And this was an assessment, GIS-based assessment, so a geospatial assessment and a quantitative analysis of the distribution of the mining sites worldwide. And we did an overlay with certain maps which map natural hazards due to floods, earthquakes, storms, and landslide, but also water scarcity, and also looking at biodiversity overlap with protected areas and sites with a very high biodiversity. And now let's have a look at the results I brought here. This method was then applied to more than 50 materials, the candidate list from the 2017 criticality assessment for the EU. And here I brought three examples which are also relevant for the energy transition, and which also Christoph showed some graphs. On the left, you have copper, in the middle, lithium, on the right, heavy rare earths. In the upper part, you can see the disaggregated results for the 8 indicators. And in this circle in the middle, you can see the lower part of the circle is an aggregated score of these 8 indicators, and you can see it's high for copper, it's medium for lithium, and for rare earths, it's in between high and medium. So for this aggregated score, there's a 5-step scale. And then in the upper left a quarter of the circle, you can see this environmental governance aspect, which also was in the first criticality analysis of the EU. It's also based on the Yale Environmental Performance Index. And you can see that there are also quite some differences. While most lithium is mined in jurisdictions with quite decent environmental performance, copper varies. It's overall, so it's a medium environmental performance overall producing countries, and heavy rare earths is mined a lot of times in jurisdictions with a rather weak environmental performance. And in the upper right is another aspect that also Christoph already highlighted, is this matter of scale, because we call it global size of material and energy flows. So lithium, the relative demand increases are impressive. However, it's mined in rather low quantities, and compared to copper, which is a very large tonnage, which also matters when we look at environmental aspects, because it's about qualitative aspects, but it's also the more you produce, the more potential for impact you have. Next slide, please. This is another more recent assessment by Eleonore Lebre from Sustainable Minerals Institute in Australia. She did a similar assessment, or also geospatial, GIS-based, of environmental, social, and governance factors, which were then also summed up to an overall score, which is the column B, and it reads like: most platinum mines have high risk for ESG issues, while lithium is less prone to this ESG risks. And on the right, I'd like to see hint your attention to column C and D. This is the aspect that Christoph already touched upon, the difference between specific demand increases. If we look, it's also a meta study. She looked at various projections of demand increase. You see this very high demand increase of about 3 to 10 times for lithium in the lower part. And copper, and we look at copper, it's in row 4. It's the demand increase for transition metals is just a very small fraction of the overall copper mine, because it's used in many applications. However, if we look in the right column, on column D, so if we translate that to tonnages, we can see there's a stark difference. Even the small part of copper, the small additional we need copper for the energy transition, it comes with large amounts. And so this is relevant when we look at environmental impact. And if you look at the bottom in lithium, this very high specific relative increase is, compared to copper, a rather low tonnage. Next slide, please. And this aspect intensity or specific impact and total impact was also considered by another recent study by our sister agency from the Netherlands, PBL, the Dutch Environmental Protection Agency, and they did also compiled available data and information on environmental impacts of producing transition metals. And here you can also see I brought two examples for freshwater use and for terrestrial acidification. And here you can also see, if you look at the specific impacts, lithium is very high up there on water use. However, if we consider the production volume, you can see that the freshwater use for copper is much higher than for lithium, for the copper production needed for renewable energies. And the same if we look at terrestrial acidification. If we look at nickel, Christoph said this example is mainly used for batteries, very high specific acidification potential. And if we include the mine tonnages, this also changes the copper. So, and this, I'm already at the end of my presentation. Next slide, please. So I'd like to wrap up the main messages of my talk, which is mining and metal production are activities of high environmental relevance. They are high-risk sectors when it comes to environment, but also when it comes to human rights violations. There are trade-offs between protecting the environment and securing supply in the short term. And these trade-offs need to be resolved. They're not resolved by not talking about them. And there are also synergies in the mid-long term. If we resolve these issues, it's a prerequisite. We can have a stable and sustainable supply, which is urgently needed for the energy transition. And in order to be able to see these trade-offs, environmental and social aspects should be considered in criticality assessments, for instance, as a third dimension. And my third message is scale matters. So production volumes should be taken into account when assessing environmental impacts. You should look at specific as well as absolute impact to have a holistic picture of potential environmental impacts of minerals and metals production. And with that, I'd like to hand back over to Christoph for the third part of our talk.
Thank you very much, Jan, for this overview on environmental impacts of critical raw materials production and highlighting the difference between specific impacts and total impacts. That question of total impacts also leads me to our results from a paper also together with Japanese colleagues. And I get back to this slide. There we go. Where we highlighted the question of what level of per capita in-use stocks can we afford in a climate neutral world that in this specific scenario follows a 2 degrees Celsius target. And I will guide you briefly through this little bit complicated graph. So we have seen here in the past per capita in-use stocks in high-income countries to low-income countries here, red to the blue line. So these are historic stocks until the year 2010 in this data set, where we have seen, for example, for iron and steel, in high-income countries, we have now about 12 tons of in-use stock per capita. So overall, the global average rises. You see here between 2000 and 2010, the largest increase of per capita stocks comes from upper and middle income countries, which is mostly an effect coming from China. And the baseline scenario, black line here, that is followed into the future centuries, is following the assumption that in the middle of the 22nd century, a saturation level around the range of high-income countries would be achieved as a global average. As Jan perfectly stated, we can only recycle what we have used in the past, so therefore this buildup of in-use stock needs to come from mostly primary raw material production. And of course, that comes with greenhouse gas emissions. So we have a already like a little bit of a conflict between building up the stocks, accepting the environmental impacts of that, and at the same time the industry needs to become climate neutral in the meantime and needs to follow a reduction target where every year a smaller global carbon budget is available for the industry. And if we draw that down to every single metal and give every single metal the same reduction target so that every metal has their fair share, right? Then we come to this conclusion that this baseline scenario would not be sufficient for a 2 degrees Celsius target because these in-use stocks are simply too high. You see here this blue wedge that opens, and I will show you that in the second slide, what that means. For both iron and steel as well as aluminum, and we had the same results for nickel and lead and copper, as well as zinc. We see a repeating pattern that a much smaller global per capita in-use stock would be available within a 2 degrees Celsius target. Now, what does this wedge mean? Our conclusion in that paper was that we need 3 aspects at the same time. We need to work with lower stocks. We need to, and that goes from the baseline level of high-income countries. With lower stocks, so using less is the first strategy. The second strategy that opens up this wedge, so allows higher per capita in-use stocks, is circular economy, and that includes all our strategies of circular economy, so longer product use, better collection and processing rates, as well as reuse of products. And we need more climate-friendly production technologies for raw materials. So even circular economy alone cannot get us to a very high per capita in-use stocks compatible with 2 degrees Celsius target, but it's the combination of using less, circular economy, and low carbon technologies that would get us there. And that already opens up like these 3 areas of action where we can address this type of paradox where we see, okay, we need those raw materials for renewable energies and environmental transition, but at the same time they come with environmental impacts. Well, we can ease this paradox a little bit if we address those 3 things. So the first one is really using less, and I will take examples from a recent research of the Rocky Mountain Institute here, which specifically looked at batteries, where they kind of showed, well, maybe those drastic statements of 10 times, 12 times, 20 times as much lithium is not necessarily true if we make technology changes, if we make adaptations to the product use, like longer lifetime and efficient vehicles and mobility. So if we combine that, then they said here in this research, basically we would be able to halve the total lithium demand with a combination of more efficient, more energy efficient, and more material efficient batteries, more efficient vehicles, longer use of vehicles, reusing and sharing those products, as well as a faster also development of the battery technologies. And we can ease that peak a little bit. And also they make this statement, we'll come back to that at the end, that if we build up a stock, this material is not lost. It is a stock that we have in our anthropogenic stock and becomes a resource for the future. Whereas if you compare that to the raw material extraction that we always have and still have for fossil fuels like oil, coal, and gas, there we burn them once and they're gone, and we have to drill or mine again. So this is not the case for batteries. We build the stock of batteries once, and we can reuse and recycle the batteries, and they stay mostly within our in-use stock. Then the second one is we need cleaner production technologies for our raw materials. And here, of course, iron is the elephant in the room. It's by far the largest and most carbon intensive in total emissions material of the metal sector and all potentially critical raw materials, although iron is very often not considered a critical raw material. But it links directly the hydrogen economy that I mentioned in my first part with the raw materials sector again, because hydrogen is our big shot, so to speak, at decarbonizing steel production by replacing coke and coal as a reduction agent with hydrogen as a reduction agent. If that hydrogen is produced from renewable energies as green hydrogen, then we would reduce the environmental impacts of steel production drastically. And a lot of steel production facilities are going into that route, replacing their blast oxygen furnaces with direct reduction agent industries now, and for now they replace it with methane, but in the future then they could use green hydrogen in large quantities. But they will also need large amounts of quantities for hydrogen for that, which then links back to, for example, platinum demand for electrolyzers. So we have a lot of feedback cycles in this direction again, but it would reduce the carbon intensity of steel production drastically, and therefore, once again, allow higher in-use stock for these materials. And we can use that in other technologies as well. And then we have the big area of recycling, where we always need to be sure about what do we really mean with recycling. And if we look at recycling only one critical raw material at a time, then we will not solve the issue. What we need is a recycling perspective, and Markus Reuter has in multiple publications has put this very, very nicely, that is product oriented. So a product consists of a variety of materials. A smartphone is a perfect example for that. A variety of critical raw materials are included, also valuable raw materials, but not all of them are very easily recyclable. Gold, copper, silver, that's easy, that's good to do. But quite a range of the critical raw materials that are also contained within a smartphone, like rare earth elements, they will currently not really be recyclable. And we need a metallurgical framework to address that. And if we look at the materials overall, closing with a periodic table, we can already see, and this is from work together with colleagues from Bordeaux, we can see that for the mass metals, the lifetime of the materials in the anthroposphere is very long. We have quite low loss rates, we have good recycling rates, we have good recycled contents in our material sectors. Of course, getting even 1% better in the iron sector simply because of its sheer size would have large environmental savings potentials. But if we look at the critical raw materials, if we want to ease their supply risks, if we want to reduce the environmental impacts there we have large potentials by at least starting with some recycling. And a lot of these are these spice metals where we're really only using quite small quantities. So you see them here highlighted in red. Gallium germanium, which we use for semiconductors, indium, tellurium, which also we use in thin films a lot. We also have scandium, which is in some very, very specific alloying elements for aluminum, but also, for example, for lithium, where a large potential can be leveraged in the future. There's quite a long road to go because it's not they are not base metals and they are not precious metals either. And therefore, they have not been targeted by the metallurgical industry so far. So there are things that we need to change. Summing up, and then going into the discussion, we do have this paradox between the energy transition and materials demand, which is apparent. We need vast amounts of raw materials, many of them critical raw materials. We grow the stocks in strategic sectors, renewable energy, electric mobility, other low carbon technologies like the hydrogen economy. And that goes once through the periodic table, the kind of materials that we need. And these strategic sectors are absolutely key industries for the environmental transition. This is also the reason why they are strategic sectors, because we need to make progress on these aspects. But at the same time, minerals are not the new oil, as the Rocky Mountain Institute put it. We have improvements in the material intensity of key technologies that are rapid. Of course, we can use that to build even larger batteries in our cars. Then we don't really save on the lithium amount, but we can also use that to reduce the material intensity of those technologies. We can use that to reduce the platinum needs in electrolyzers. We can use it to reduce the neodymium need in wind turbines. And as a second point here, the transition to renewable energies has absolute and amazing co-benefits because that supports low carbon production of critical raw materials, which will then make them even better in terms of their environmental transition potential. And the critical raw material stocks that we build today are the resources of tomorrow. Because by building this stock now, once we already start the circular economy, even before we have the technology or the recycling capacities at scale. So the environmental issues with critical raw material production are important to address, yes, but let's not forget, this should not be a reason to say that's why we're delaying the substitution of fossil-based technologies. These materials are key to the environmental transition, and with using less, more recycling and lower carbon technology production, we will be able to make this transition in a sustainable way. And we're very much looking forward to the discussion with you now.